Hi everyone. Today we have a very interesting pleasure lecture. It's about something interesting, something pleasure. It's about smile. And you know what is smile in foundational mathematics? It is implied volatility. So let's get started. But previously on stochastic financial mathematics, maybe you remember that we formulated the main aim of our course to model financial market. And it means that we need to model riskless active, and it's easy. And second, we need to choose geometrical Brownian motion as a model for risky asset. Yes, riskless and risky, and you see this differential equation which describes the geometrical Brownian motion, where Wt is the Wiener process of Brownian motion. After that, we used its lemma to calculate derivative from f, where f is some pio function of call option. And it was this formula. After we build the riskless portfolio from two positions, -1 means that we sell one option, and plus df respect to dc, ds means that we buy this amount of stock prices. And the value of portfolio we can calculate using this formula. And assumed that the change on portfolio is equal to this product, we arrived at a celebrated Black-Scholes partial differential equation, and for boundary condition, we obtained Black-Scholes formula. You remember this formula. Last lesson, we would like to answer the question, what happens with option price if one of the input parameters changes, and we get the table which describes the sensitivity of Black-Scholes model, and it was Greek letters. And we provide dynamic delta hedging strategies. What we know about Black-Scholes model? We know that the Black-Scholes formula is arguably the most important and famous formula in all of finance and economics. It's used extensively in the financial industry. It has led to enormous amount of academic work, science, and its publications. But we will see how it's used in practice. But yes, but everyone knows that geometrical Brownian motion model is not a good approximation, and everybody knows this. This was the assumption of Black-Scholes model, and assumption of the market and assumption of the asset. And you remember that in the assumption of the asset, the second assumption was about random walk, and you remember we spoke that the log returns is a random walk, and we will assume its drift and volatility is constant. But it's not true, and there are the holes in the assumption on the Black-Scholes model. It is the one ideas of today's lectures. Today's lectures is about the holes in the assumption and what we can do with this. Even Black who is creator of the one of the creators of this formula, he wrote that the people like the model because they can easily understand its assumption. The model is often good as a first approximation, and if you can see the holes in the assumption, you can use the model in more sophistical ways. Um, so what does it mean? In this formula, we have 5 parameters. You remember about this. T capital, it is time to maturity, to exercising of the option. And it is clear, and we can do anything with this. Time is time, yes. Um, the second parameter is K. K, it is strike price. And this price is pointed in the option, or we can choose this price on this side. So it is fixed parameter, and we can do with this anything. The next parameters are capital and its annually interest rate. We have question to it, but more or less it's constantly parameters. The next parameter, it is as its initial price, and it is exactly what we can see, what we know about the today's price. So we cannot do with this anything. And the last parameter, it is sigma volatility. What is volatility? It is annual variance for logarithms. Yes, you remember. We can compute variance for logarithms, and it is a daily variance. But if we multiply this daily variance by 254, it's amount days in the year. So we obtain the volatility. Volatility, it's about in diapason from 10% to 90%. No, it's approximately. But there are some questions for these parameters, because if we have for computing, for example, 100 days, we get one volatility, one value. Yes, if we have 150 days, it was another volatility. If we have 300 days, it's another. No, we can compute another value of volatility, but what of this volatility is right, we don't know. We don't know. Um, so volatility. Volatility is a measure for a variation of price of a financial instrument over time. It's clear. It's clear. It is on this slide. You can see how we can calculate this volatility. The volatility per day is the standard deviation. The volatility per year is 252 times the daily volatility, and after that we should to take a square root. Um, and on this slide, you can see how we can do this in the Excel. We have data, the first column, the second column, it is the prices, the second, it's the logarithms. The next, it is the difference between the second and first, the third and second, yes, and um, after that, no, and from this column we can calculate variance. We can only use function in Excel variance, or we can do this by a formula. No, formula, you can see this formula. Um, and after that, we can multiply this by 222, and after that, to take a square root. Oh, sorry. No. Oh, it's our slide. it's our slide, and that all is clear. Yes. Um, and in your individual task, um, you need to compute fair price for call and put option. And for this, the time is given. Yes, it is amount of day divided by 365 or 252. It's up to you. After that, we need to compute D1, D2, the cumulative function of normal distribution from D1 and D2, and after that, to use Black-Scholes formula. And so on this picture, you can see that for November, we have this value for call option. For December, this value is grow, is more. Yes, it is 0.58, but for December, it's 3 and 12. After that, this value 4 and 46, and finally for April it is 7.62, for example. Yes. um, it was our parameters, and now we can to compare this theoretical price, what we just have computed using Black-Scholes formula, and real price. Real price, it is price from Nasdaq side. Yes, and you see that theoretical for November 0.58, but real price 1.2. For December, it is different 3.9, and really it is 4.46. And so you see that these prices aren't the same, doesn't coincide. Yes. For put option, the situation is similar, but even the difference even more than the call option. Yes, you see, you see. Uh, so so why formula Black-Scholes doesn't work well? It is the reason is volatility. The reason is volatility. But what we can do? We can we can to assume that we can assume that volatility isn't constant, but its function. For example, from T, but in other cases, we can assume that not only from T, but from random, from other parameters. And what we can do? We can consider formula Black-Scholes as function from these 5 parameters. And for example, the results of formula Black-Scholes, yes, it is 0.58. You see, yes, theoretical fair price. But you see that real price 1.2. And if we in this formula replace the result 0.5 by 1.2 and solve this equation respect to volatility, we get another value of volatility, and this value is called implied volatility. Do you understand the idea? Do you understand? Maybe I repeat. We have formula Blacker shows, and we can consider this formula as function of 5 parameters, T, R, and so on, and sigma, and sigma. And the result, for example, of this formula is 0, 0.585 and so on. But if we now solve this equation respect to sigma, we can get the another value of sigma, because when we computed this, the sigma was I don't remember, but we can have a look. It was the current price, the strike price, there is, oh, the price volatility was 0.28 approximately, yes. But if now we know the result, we can solve this equation and get sigma, and it was another value, and this value is called implied volatility. Okay. So implied volatility of an option contract is that value of volatility of the underlying instrument, which when input in option pricing model will return a theoretical value equal to the current market price of the option. No, you understand. We replace theoretical value by the current market price of the option, and we solve this equation and we get implied volatility. What's interesting that the share option traded in American market didn't show a volatility smile before the crash of 1987, but began showing one afterwards, after this crash of 1987. It is believed that investor reassessment of the probabilities of fat tail have led to higher prices for out of the money option. This anomaly implies deficiencies to the standard Black-Scholes option pricing model, which assumes constant volatility and log normal distribution of underlying asset returns. Empirical asset return distribution, however, tend to fat tails, kurtosis, and skew. So, how we can do this in Excel? In Excel, we need to choose data after this option, what if, and after this find parameter, and we replace the result by the price from site, and no, what if, yes, and we would like to find this parameter. For example, it was price. It was November, December, and it is a result where we have call option and implied volatility in this. This is volatility. So we choose data and what if result will be this, and the volatility was changed. We can try to do this in practice lesson. And in such a way, we can get implied volatility smile surface of smile effect. Um, in this slide, you see this volatility smile. It is a graph, and x, y-x, it's implied volatility, but x axis is strike price, and why it's important? It's important? Because volatility describes risk, such parameter as risk, and from this graph we see that the less value of this implied volatility, for example, in this in this point, and we can define what strike price is the most riskless. Um, the implied volatility is in the shape of a smile with the minimum value. Yes, what it's the minimum value. It is the minimum value uh, for the money option, and the volatility rising as you move on either side, as shown by the plot below. Right, on left, yes, the implied volatility is rising, so the risk is growing. Um, this minimum value always coincides with price at the money, at the money. Um, and right in the money puts, out of the money calls. Left, if we consider put option, out of the money, if we consider call option, in the money. And you see that volatility increases as the option becomes increasingly in the money or out of the money. What does mean out of the money? OTM, ITM, ITM. I can explain it. Suppose that the current stock price of company IBM is 100. So it is price for today, yes? And if we choose a call or put option with a strike of 100, or very closely to this, it calls that we are at the money. Our call option at the money, Um, let's consider another situation. If we choose call with a strike of 80, 80 is less than 100, and it is in the money, And for your function, you remember, for your function, it is S minus K. Um, so S minus K, it is 20, and dollars, yes, and it is more than zero. So if we have profit, no, or for your function more than zero, it's called that we have a call option in the money, but if in this situation we consider a put option, and you remember the for your function of put option is opposite strike price minus current stock price, and its negative value, Um, so this put option is out of the money. so for stock price 18, there are two situations. For call option, it's situation in the money, but for put option, it's situation out of the money. And we can consider another scenario if call option with strike price 120. So for call option 120 is situation out of the money because 100 minus 120 is negative value, so it's out of the money. But for put option, it's opposite is situation where this put option is in the money because because for your function for put option it is strike price minus market stock price 120 minus 100, it is a positive value, and so this option in the money. So it's about smile smile effect of volatility and how we can do this in Excel. Mm, we can use Python library Median, and in this case we importing libraries. It is from Skype stats important norm. Um, import Pantas SPD and install Median in this way. And after this, a very interesting syntax of this function bs it's because black shows. So for example, we write c equals mbn point bs, and after that we need to input parameters. And you understand parameter, and you remember parameters. The first parameter under underlying price, it is stock price. For example, it is stock price for today, 8,572. The second parameter, it is strike price. Strike price, it is price of what is pointed in your option. For example, it is 8,700, and you see that it's close to underlying price, or to stock price, and maybe it's at the money, but difference there is no and interest rate, it is in this case it is 0.5, but it's not exactly right. And after that the days to expiration, it's only amount days, not the value in the years as in formula Black shows, but the amount of days. And volatility after that we can print call price for this option, put price, call delta, put delta, call theta, call delta, no, and so on. So we can print call and put price, and all of these Greeks letter. You remember sensitivity of these formulas, yes? How using this function in MBS we can compute implied volatility. In this case, we can input as parameters all this as in previous. Yes, it is underlying, strike, interest, days to expiration. It's the same, you see. Yes, it's the same. But after that, write not parameter volatility, but for example, call price. call price. We can take this call price from Nasdaq. Yes, from Nasdaq. And after that, we can print implied volatility. You see that it's very easy. Yes. Um, so I would like that you learn uh, how you can do this as in Excel as in Python. Do you have any questions to the syntax of this function? No?
No.
And and now what can we do with this? How we can to model volatility? Modeling the volatility smile is an active area of research in quantitative finance. A method of modeling the volatility smile includes stochastic volatility models and local volatility models. And I can explain about this. A local volatility model in mathematical finance and financial engineering is one that treats volatility as a function of both the current asset level ST and time T. So in model Blecker shows the volatility is constant, but we can consider volatility as a function of two parameters, T and ST. Yes. As such, a local volatility model is a generalization of the Black-Scholes model, where the volatility, no, yes, is constant. This concept of local volatility was developed when Bruno Dupuy, its French scientist, noted that there is a unique diffusion process consistent with the risk neutral densities derived from the market prices of European options. And it is very often we can consider the model for stock price in this form, ds divided by s, where s is function from t, equals rdt plus sigma as function from s, t, and t, and derivative from Wiener process. Yes, so it is as geometrical Brownian motion. There is only one difference in geometrical Brownian motion. Sigma is constant, but this sigma it is function from two parameters. So if it's not constant, we should to find out what is this, how we can model this sigma. And for example, it's only one example how the scientists can model this stochastic volatility. For example, it is the process when which can express in this form that on the left side you can see square of volatility, a function of k and t, where the k it is strike price and t capital it's time to maturity. And on the right side, you see numerator and denominator, and in numerator and denominator, you see the derivatives, and it is as Greek letters, yes, ds, dc to respect to dt, C change if change time to maturity, uh, have C change if strike change, and the second derivatives. And it's the one way how we can improve, adjust the Black-Scholes formula, how we can to take in account that the volatility isn't constant but function from S and T, for example. So it's a random function. It's stochastic process. And maybe that's all for today. And my reference it's the book John Hall, Option Futures and Other Derivatives, and you can find this in Distedu. And it is article Bruno Duperret, Pricing with a Smile, and it is the site where you can find how to do this using Python. Uh, and um, and that's all. Thank you for your attention. And maybe you have any questions, please don't hesitate to ask me. What do you want to ask? Everything is clear, yes? So after today's lecture, you should to find implied volatility using Excel and using Python, and to construct graph which demonstrate a smile of volatility, and you should to do this on your practice on your problem set. And now maybe you have some time to do your test about this lecture. Yes. So I wish you good luck, and if you have any questions, please do this.
Okay, everything